So welcome back. Today we talk about changes in A-1 from changes in A. And this maps section 3.1 in Professor's Strang textbook. So this is the outline of the presentation. We'll first talk about perturbing the identity matrix and its impact on the inverse of the matrix. Then we'll talk about perturbing any invertible matrix A and how we can retrieve A-1. We'll shortly talk about updating least squares, and hopefully we can reach the Kalman filter introduction. Okay? So the question here, what happens with A-1, I mean the inverse of A, if there are small changes in it, there are small perturbations in it. So for example, let's start with something simple. Let's start by subtracting a low rank matrix from A. Okay? So in this section, we try to estimate the change in eigenvalues and the change in singular values. We will find, in fact, an exact formula for the changes in A-1. So let us start with some notes when A equals I, and the changes are of rank 1. So there are just tiny and small changes in A. So for instance, let's define M, and this matrix M will be with us during the whole section. Okay? So which is equal to I, the identity matrix, minus UV. Here, U and V are two vectors of one column. So UVT basically is a one rank matrix. So the right formula to get M-1 in that case is given by I plus UVT divided by 1 minus VT. Okay? Of course, here at the denominator, you are getting a real number. So you can notice here that the correction in M-1 is also of the form UVT, but divided by 1 minus VT. So it's also of rank 1. The correction term, which is here, the correction term, the whole thing, which we can let me use another color. This whole thing, which is the correction term, this is the correction term, can also be infinite. So in that case, we will have M, which is singular. Singular means non-invertible. And this case happens especially when you have VTU, which is equal to 1. Okay? So you gotta be careful. The simplest proof that this works, and this is the right formula, is just to check that M times M-1 equals I. In fact, it's easy to see that when you multiply M by M-1, you here on the left side you have M, which is I minus UVT, and on the right side you have M-1, which is I plus UVT divided by 1 minus VTU. So if you just expand here, you're going to have on this side I multiplying I minus UVT, so you're going to have I minus UVT. And the remaining part is just 1 minus UVT multiplied by the correction term, which is here. Right? So what happens here in the numerator, you see that you'll have UVT, okay, minus UVT times UVT. So you're going to have 1 minus UVT divided by 1 minus UVT. Okay? So basically, you're going to have, this is what's going to happen. Okay? So basically, you have a simplification in the fraction here, which leaves you just with UVT, okay? Which means that you're going to end up with I. So this way, you just verified. In fact, this is not let's say the exact proof or the exact construction proof on how we get M-1. But the things get a little bit more complicated when the changes in the matrix I are of larger rank. So let's, for instance, suppose that the perturbations UVT are now frank K. So now U is what? It's no longer a column vector. So it's N by K, and Vt is K by N. So once you perform the multiplication, UVT, you end up with a square matrix. A square matrix which is N by N, in fact. So we have K columns and K rows, in fact. The inverse of M here could be written by I index N and minus UVT. So this is the perturbation, UVT, and think that here we have chosen UVT with capital letters just to emphasize the fact that we are now dealing with matrices, no longer with just column. So the right formula here is M minus 1, which is I index N. So it's the square matrix I with N rows and columns, plus U times I index K. So this is the identity with dimension K minus VTU all times VT. Right? And you can see that, in fact, we are exchanging an inverse of size N with an inverse of size K. So basically, we are reducing with this formula the dimension of the problem. Theoretically, we are reducing the dimension of the problem. So let's see it for the first example. So for the first example, which is here, we have M, which maps the change in I. So remember, here we're starting with the simplest assumption that K is I. Yeah? So this matrix, which is 3 by 3, and you can see that the 2 and 3rd columns are exactly the first column, and this is equal to, in fact, U times VT. Okay, so this is the perturbation. You just subtracted 1 unit from all the entries in I. So to map this change, in fact, you could use the fact that, well, U equals VT equals 1, 1, 1, in fact. And if you perform the multiplication now, in that case, U as a column times VT, 1, 1, 1, you retrieve exactly this matrix, which is 3 times the column 1, 1, 1, 1. Okay? So we can see that if we apply the formulation, which is here, what am I going to have? I'm going to have the first example. I'm going to have I plus UVT divided by 1 minus 3. Okay? So let me just check something. I think there was a tiny typo here in the formulation. I believe there is a negative 1. I think it's a negative 1. It's not. So where are we exactly? Page 166. Yes, it's a negative 1. So here it should have been a negative 1 here. Okay. So this is the inverse of IK minus VT. This should have been. That's why we're going to have 1 minus 3. So if you redo the computation here, you're going to have n minus 1, which is equal to I minus half of that matrix, which is 1. And it's easy to repeat. So basically, the inverse of this matrix is going to be 0, 5, minus 0, 5, of course, on here, on the first, to complete the first row. Similarly, to complete the first column, if you wish, and you understand perfectly what's going on. So you just performed an inversion without much ado. Okay? Here, exactly the same terms, and okay? If you wish. So immediately we have 2 easy formulations. First of all, the first one maps the changes in m minus 1 when I is equal to A, and the change is in rank 1 or in rank K. We have the formulation. Okay? So hopefully it's clear, but we are aiming for more. So for more details, here this is what's going to happen. So here I'm using a second example. Now the changes are a little bit more tricky. So I'm saying that U is equal to 1, 0, 0, 1, and 0, 0, and Vt is equal to 0, 1, 1, 0, 0, 1. So if you perform the operation U times Vt, you're going to have this matrix, which is the perturbation matrix, 0, 1, 1, 0, 0, 1, and 0, 0, 1. Okay? So now VTU, on the other side, if you, let's say, do the reverse product, VTU, we're going to end up with a 2 by 2 matrix and not a 3 by 3 matrix. So you end up with 0, 1, 0, 0. So in the formulation, I said that m minus 1 is equal to I plus U times I2. See here, this is K because we have changes on of rank 2. Minus VTU to the power negative 1 times Vt. So you can end up with here I replaced I by I3. Here I placed U. And here I just inverted this matrix of rank 2, which is I2 minus VTU. Okay? You're going to end up with this matrix. 1 minus 1, 0, 1. And multiplied by Vt, I get this answer. So this is the inverse matrix. Okay? And it's easily done in 3 to 4 steps. So the whole point is that you are again reducing the dimension of the problem. Instead of working on the inversion of, let's say here, a 3 by 3 matrix, you just work with using the result of the inversion of a 2 by 2 matrix. So the whole point is that the 3 by 3 matrix M-1 came from inverting that 2 by 2 matrix, which is here, which is between the two brackets, which is I2 minus VTU. Okay? So it kind of lowers the complexity of the problem you're trying to solve. Okay? And it basically yields a problem which has the same order of complexity as the rank of the changes in your matrix. Okay? Is it clear for everyone? This first part?
I have a question.
Yes, go ahead.
How can we find U and V?
Well, here U and V, if you know the perturbation, you just perform a U-VT factorization, if you wish. First thing, and then you can work with these. But basically here you are just mapping. In fact, if you look to the perturbation, it's much more simple. You are trying to identify the independent columns. Am I right? Okay. So you can just use a simple CR factorization. Is that okay? So for example, here in the previous slide, when the perturbation was based on only one single column, you see? So basically what did I do? I say I'm taking first column as U, which is 1, 1, 1. Okay? And it's just going to be multiplied by 1, 1, 1. Okay? That's why I'm saying that Vt is equal to 1, 1, 1. So this y is Vt. And this is simply a CR factorization, in fact, because column 2 is same as column 3, which is the same as column 1. Just reproducing here. Get my point?
Yes.
Okay. Now, for the next example, basically here you have two linearly independent columns, which are here, column 2 and column 3. Column 1, in fact, is just a 0. Okay? So to map this, basically you have only to take, for example, here I can change it a little bit. I can say that I'm taking 1, 0, 0, which is column 2. I'm taking 0, 1. I think there is a small typo here again. I didn't review one now. Yeah, I think so. This should have been a 0, 1. So why am I doing that? Because you can map this one. You can the one that is here. You can retrieve it. So if you multiply it by 0, 0 first of all. So sure, you're going to have a whole column of zeros if you do the product. Here I'm going to have a 1, 0, and here what I'm going to have, I'm going to place 1, 1. Why am I doing that? Because if I sum up column 2 here in my CR factorization plus column 1 and column 2, I'm going to have exactly this. I'm going to have 1, 1, and 0. This item is 0, guys. And the last item in the matrix, which is here, which has crossed, is 0. So you see how did I find Aziz? Okay, so you can just basically do a CR factorization and you're done with it. Okay? But be careful, as we mentioned in the previous slide, these formulas don't work if you basically, for example, end up with here. So this should have been a negative 1. This is what we corrected. If you end up with a non-invertible singular matrix here, of course, you cannot go much further. Do you get my point? Similarly here, if you end up with 1 minus VTU equals 0, you cannot go much further. The formula doesn't work. Okay, so we're done with two first examples, one with rank 1, the second one with rank 2. And now we move to a more general result. And this is the main dish. It's really beautiful that in fact we were able to generate a matrix that in fact gives directly the inverse of the perturbed matrix. So we started in fact with A instead of I to explain what's going on in fact and how we can verify this formula. But now in general, if you suppose that M is a new matrix you get after perturbing A, and this perturbation is in fact due to two vectors or two matrices U and V, such that M writes as A minus U VT. Now the right formula to use for that is M minus 1, which equals A minus 1. So basically it uses the previous information, plus A minus 1 times U. Now you're going to multiply by an inverse matrix, which is I minus, this guy is I, not 1, not to get confused with 1. It's I minus VT times A minus 1 U, all inverted. And now we continue with the multiplication, VT A minus 1. And I will detail a small example. So, but here I attract your attention that you can multiply here just M by I minus 1 to verify that you end up with the identity matrix. So for example, this is a problem from the textbook. I'm using it just to detail what's going on. So here is exercise 3, page 166, and it tests the SMW formula on the original matrix, which is A3002, with just a simple rank 1 change, first of all. The only difference with the examples we've solved before is that now this is no longer the identity matrix. A is no longer the identity matrix. Okay? You see, the diagonal matrix is 3002, but it's not the identity matrix. So you could notice that here that UVT is rank 1. And if you are seeking M, so M is in fact A minus UVT. It's 2002. So one can think right now, well, if the problem is to find M minus 1, well, it's easy. So the goal is to make it easy to verify that the formulation gives you exactly the answer. It's easy to verify, in fact, that M minus 1 is equal to 0.50005. So this is the target. Now, in the next, we're going to detail. I'm going to move to the whiteboard, and I'm going to detail how we can find this using the formulation. Is that okay for you? So let me share with you the whiteboard. Hopefully, it's going to be much clearer. So I'll be writing in blue. Okay. So here we said that A is 3002, and we said that U is 10, I guess. 10. The column vector, and VT is 10. So first of all, you've noticed in the formulation that we needed A inverse. So basically, you can see that A inverse here is easy to track. which is, you see that the determinant here is 6. So the A inverse is going to be 1 over 6 multiplied by 2, 0, 0. Am I right, guys? I think it's pretty obvious. Okay, you can write it also in fraction form. So it's going to be 1/3, 0, 0 half. So now let's see what the formula writes. The formula said it's equal to m minus 1 is equal to a minus 1, which is here with us, plus a minus 1, which is in fact an updating of the inverse of a. Plus, it's multiplied by u here, and here we're going to place the identity matrix. But wait a second. What should I write here? Should I write I or 1? Since the change is of rank 1, instead of I, I'm going to place 1, because this is the identity or the natural element of the product in the real space. We are not using I2 here, okay? We are using, or IK, we are using 1 instead of I. Why? Because the changes are of rank 1 times VT A minus 1 U. Did you get the point, guys? Everyone? Here, I place it 1 instead of I from the formulation I borrowed. So, and I end up with VT A minus 1. And that was the first trick in this exercise. Okay, so now let me continue. Here I'm going to place the inverse function, which is 1/3, 0, 0, 1/2. And if you do it on your side, you can easily now verify that it's going to end up with the same result. You're going to end up with 1/3, 0, 0/2. Here, I'll just place it again, inverse. Here, u to me is 1, 0. And between brackets, I'm working on the inversion, but basically I'm just inverting a real number. I'm going to write 1 minus. Now, what do I have? In fact, I have 1, 0, which is VT, times A minus 1. So forgive me for not now writing it to save space. And I'm going to have 1, 0. I wrote it twice already. It's fairly enough. And inverted, multiplied by, again, 1, 0. So a whole long formula for this simple operation. But the intention is just to do the exercise and see that the formulation works well with something we can easily check. So I'm going to have some partial results here, okay, to save my time. So first of all, I'm going to change the color. Here, the result of this product is going to give you 1/3, 0. It's a 2 by 1, in fact, factor. You can easily check that it's okay. Okay, I'm going to just bring this A minus 1 to this line. Okay. Now, what's happening here inside the brackets? I'm having 1, 0 multiplying A minus 1. So basically, I'm having 1, 3, 0, 1/3, 0. It's 1 minus 1/3, 0. This is the result of whom? The result of this product, okay, which is here, multiplying 1, 0. And I'm going to place inverted, okay, and I'm going to place the result here of also of this product. So I saved a lot of effort, and my operation is neat. I'm going to have 1/3, 0 also. Right? So how much is this real number now I need to invert? It's in fact 1 minus 1/3, because if you perform the product, you end up with the real number 1/3. So basically, the inverse of 1 minus 1/3, which is 2/3, is going to be how much? It's going to be 3/2. So the whole inversion here brings 3/2 multiplied by 1/3, 0. and multiplied by 1 over 3, 0. Okay? Of course, you are expected to find a 2 by 2 matrix here. Okay, so you can, if you wish, you can bring the 3 over 2 outside. And this is M minus 1. I'm using different colors so you can notice the difference in the steps. Okay, so how much is the result here? I'm going to have 3 over 2 times 1 over 9. Am I right? It's going to be 1 over 3, 0, 0, 1 over 2. And I kind of have the luxury to place 3 over 2 outside. And here I generated this matrix 1 over 9, 0, 0, 0. Now, how much is 3 over 2 times 1 over 9, guys? 3 over 18, am I right? Which is 1 over 6. Okay, so this guy, the product here, if I perform it, is going to give me 1 over 6. 1 over 6 plus 1 over 3 is 1/2. And this is what I expected. I expected to get this result 1 over 2, 0, 0, 1 over 2. Okay? Which verifies exactly what I expected. Is that okay for everyone? Any question? Any step I missed, guys? No questions means everything is clear. Okay, so later on, you can verify that everything works fine. Okay, shall we move forward?
Yes.
Okay, so let me get back to now to the file. So we were exactly here. Hopefully, we just solved this this problem. Okay, so we just detailed this problem. Okay, so let's move forward. Now, so let's see what happens with the previous method, like the updating the least squares. Okay? In fact, in section 2, if you recall, guys, not that long time ago, I think it was almost 2 weeks ago, we discussed the least squares equation. The second way was to use what we call the normal equations, which is based, if you remember, based on the projection. Okay, the projection of B on the plane of the Kalman space of A. So, so let us suppose here, and here this is where things get more interesting. So let's suppose that a new equation arrives in your linear system. A new equation, a whole new equation. Okay. So now A has a new row, and we're going to call it R, which is 1 by n. Okay? And there is a new measurement which maps this new equation or this new condition in your model. The new solution you are supposed to find is solves ATRT times AR. So this is the updated system, and the new solution, which is X hat, which in fact should map the following: that ATRT it is equal to ATRT, and the new column here on the right hand side is B, and you added the new measurement M as well. So first of all, updating the least squares yields a new normal equations. If you see here this product, it gives you ATA plus RTR. And as you can see, if you're talking about bringing a new row R, which is 1 by n, in fact, you are bringing a rank 1 correction to ATA. Okay? So now, in fact, the work is no longer on A. It's on the inverse of ATA. The matrix you just updated is ATA. So to update X hat, in fact, we do not want to create and solve the new system from the beginning. We could be working on an updating formula. So for instance, we can use this formula to invert the new Kalman's equation matrix. So to invert ATA plus RTR, you can use this fact that in fact it's equal to ATA minus 1 minus C. C, well, in fact, is 1 divided by 1 plus R times AT A minus 1 RT. And this is borrowed exactly from the formulation we just seen before. Okay? One with the rank 1 formulation. Multiplying 88 inverse times RTR times 88 inverse. Okay? And it works fine to update the solution for your system. And this way you can find what? Find the new solution X hat. Okay? So to illustrate this fact, let's take one example. So in fact, you are solving just quickly a new system. You need to solve just a partial system to update the solution. This is what it said, to find C. Okay? So in example 4 from the textbook, in fact, we use the solution we just found in the previous exercise, which is exercise 3, the one which had the 0.5, 0, 0, 0.5, okay? And we are just adding here, they're giving us the freedom to choose any right-hand side measurement column, let's say D, okay? To solve the updated system, which is my equals, and compute the new solution. In fact, the algorithm to do that is decomposed in 2 simple steps. So first of all, you start by solving the old system you have, which is AX equals B. Why do you need that? Because you need it to update the new solution. And now, if you brought a change which is decomposed with rank 1 perturbation using V and U, this is U and this is V. Okay? First of all, you solve a new system which is AZ equals U, and you use this solution Z to compute a scalar number which is D equals 1 minus VTZ. Very small typo. 1 minus VTZ. So you see that U and V, which map the perturbation, they were brought to use D. Then you can easily update Y using X plus VTX over D times is the solution to your new system. And you can finally verify this. Okay? So for instance, if for my old case here, for exercise 3, if I use VT, which is 3.2, so basically the system I had before, if you remember, was 3.0.0.2. Okay? This was the old A I had carried with me in example 3, exercise 3. Times X equals 3.2. What is the obvious solution here? It's 1, 1. Am I right? So X1 is 1, X2 is 1. Am I right? So this first step yields xt equals 1 now. So we just solved here the first step. And if similarly, now you can also map the change. Remember, we already had U and V from the previous case. It's 1, 0, 1, 0. So we can also find Z that solves AZ equals U. So ZT, in fact, is 1/3 0. And similarly, you can compute, to complete the first step, you can compute D, which is 1 minus, in fact, 1/3 0, which is Z in column, times VT. Okay? So you're going to just have a real number, which is 1, 0. So basically, it's 1 minus 1 over 3. So you end up with D, which is equal to 2 over 3. Okay? Now, all I have to do is to compute Y and move on to the second step, which is going to be equal to how much? It is 1, 1, my solution, plus VTX. VTX means 1, 0, multiplied by 1, 1, divided by 2 over 3, multiplied by Z, which is 1 over 3, 0. And here we end up with YT, which is 3 over 2, 0, which in fact solves the system, as you can see. With these 2 steps, you can see that it solves the system, which is 2, 0, with the updated A times Y equals our D chosen here, which was 3, 2. You can easily see that it works quite well. The updating is what you can see that 2 times 3 over 2 gives 3. And on the other side, you have 2 times, should have been 1 here, sorry. should have been 1, not 0. But I'm not that stupid. Sorry for that. Okay. So here you can easily work it in details and just 2 simple steps. Do we need details for this, guys? As you wish. It's up to you now. Okay, so so you can see that now we worked on the updating of the least squares formulation. Okay? So let me move on to the last part. In here, in the last part, we introduce what we call the Kalman filter, and it's probably one of the let's say most fascinating results. Kalman, in fact, noticed that this update idea could apply to dynamic least squares. In fact, what do we mean by dynamic? It means that even without new data, the state vector x could be changing with time. Okay? This might be due to some velocity. So if x is given the position of a GPS satellite, that position will move by about delta x, which is v, velocity times delta t. Okay? And this approximation, or better one, would be the state equation for xn plus 1 at a new time. Okay? So in fact, a new measurement bm plus 1 at a new time, which is t plus delta t, will further update that approximation position to a new solution, x new. So in fact, we are now adding 2 new equations, a state equation and a measurement equation. Okay, not only one. So the new system will be written as A, which is the old system matrix, 0 minus I, 0 R times the x old, x new current, and should be equal to B, the old measurement. First of all, you should put the new, insert the condition on the fact that you are satisfying the delta x equation and the new measurement equation. So basically, this is the state equation that you are mapping, that we are talking about it. This is the state equation we're talking about, and this is the measurement equation you have. Okay? So this is the new idea. So we're working with dynamic least squares. So, but the idea here now is that we want the least square solution to this equation. But what makes the Kalman filter, in fact, truly impressive is that the state equation and the measurement equation have their own covariance matrices. So these are not, in fact, exact equations. They have some kind of reliabilities. Okay? They have reliabilities, and we do have what we can call variance and covariances, which measure the different reliabilities for these equations. So if you go back to the old way we solved for the least squares, the normal equations, if you remember, in 2.2 were written ATA x hat equals ATB. Now we introduce this weight, which is due to the variance, and we place it to, in fact, to take into account the fact that the perturbation is added to say that, well, there is some kind of reliability on the system we need to solve. And in fact, with the Kalman filter, V itself changes with time. Okay? Changes with time because you have more information, and you have more information on the variance covariances. So, in fact, Kalman, what it does, it updates the x old in 2 simple steps. First of all, the prediction comes from the state equation. Then comes the correction. of the prediction. Let's say we're saying we are learning from data. We're learning from our old mistakes. So we are adding a correction. Then comes the correction to x new using the new measurement p n plus 1, which in fact you mean it intends to reach this target, the zero correction. Okay? And you end up having what we call a Kalman matrix. Kalman matrix, which is the Kalman gain matrix, which could be written this way. It's in fact, let me take it to the side. I'll write here. It's in fact x hat new, the new x hat is equal to the x state plus k, the Kalman gain matrix, multiplied by the measurement Pn plus 1 minus r, the correction times x hat. Okay? So this is the formula we'll be using. Okay? Hopefully we'll come back to this next time and give some examples on the use of the